about magnetic flux that will appear in the exam. There will not be any questions on induced EMF. In the other class, we went through this next couple of pages, and I want to screen capture this so that it goes up onto YouTube. So far, we've looked at electromagnetic force. We used the Lorentz force to figure out that if we have charges moving through a magnetic field, the right-hand rule will tell us the direction of the force, and this is going to be useful for motors. But then, if we go backwards, if we input some mechanical energy and get our wire moving through a magnetic field, then we can move charges through the wire, and charges will move essentially. They don't want to move, they'll have energy in a field, they will have a voltage. So this is going to be our example for generators. And we have some equations. We've got Faraday, probably should be capitals, Faraday and Lenz. We will get to that. Maybe we'll start off today with Faraday. So, could we please have a look down here? If we were to move a wire, a length of wire of dimensions L through a magnetic field. Now in this diagram it's directed into the page, and we're sweeping this wire across with a certain speed V. Okay? Can we close the laptop? Thank you. Now, we can still use the right-hand rule, but we've got to be careful. I'm going to call this the right slap rule. Consider just a lone single positive charge. There he is there, red plus sign. So he is a positive charge stuck in that wire, and he's going along for a ride. Okay? Now, so we've got our V going that way. So I would like you to consider your positive charge moving that way. So, your thumb, please point it to the right. Your fingers, please point the fingers into the page. As it's moving, those positive charges will get forced upwards. What you will find is that the positive charge will accumulate at the top end of this wire, but really, we actually know it's because the electrons are being pushed down to the bottom end of the wire. So we will accumulate a net positive charge at the top, and we will accumulate a net negative charge at the bottom. Now, mobile charges do not like existing next to their like-charged brethren. They would rather just spread themselves out equally along the wire. We are forcing these guys to be where they do not want to be. Okay? So because we've crammed all of these electrons down there, and they're all going to be repelling each other with a certain electro-repulsive force, they have a certain amount of electrical potential energy due to their state or position in an electric field. And we measure that electrical potential as voltage. I could come up with a certain device that could measure the difference in electrical potential from one point of my wire to the other, and it would say voltage. Okay? So what we have done, we have set up a potential difference. Okay? But only while the wire is moving. One thing, Aaron, I'd like you to consider is these electrons, as you push them down while the wire is moving, you're cramming them down. Think of them as little springs that you're compressing. Little springs that you're compressing, little springs that you're compressing. You are doing work. You're storing it as elastic potential. When it stops, they all race back. Now, there's so many ways that you can think of this. If you're moving charges through a resistance, you're converting energy into heat. And as they race back, you're converting energy to heat. Not only that, as you move this wire through the field, you are putting in a mechanical input. You are doing work. You will feel a resistance. And we will set up some scenarios throughout the remainder of the course. As you move it through a magnetic field, it suddenly feels more inert. It feels heavier. You can actually feel the resistance. Okay? If I move this at a constant speed without any input of energy, and all the electrons suddenly went, you know what, I'm going to exist over here, we're violating conservation of energy. There's a certain amount of energy that goes into moving all of those electrons down there, and so you're converting mechanical energy into electrical. Okay. Now, this is a little bit of a stretch to get the equation, but I want to show you a cool equation that we can get. We know that work done on a charge can be measured as QV, where V is capital voltage. Okay? We also know that work done can be equal to F times S, mechanical force multiplied by the distance displaced. So let's just propose that we are forcing an electron down with an F equals QVB, and we're moving at a certain length, a certain distance. So I'm going to say here that F equals QVB. Okay? So I could say, well, hang on. I know that QVBL also equals QV, and a cancely, we get this nice equation that capital V for voltage, please do not confuse V for velocity and V for voltage. And so to not confuse the two, we're going to write epsilon equals VBL. This is in your data sheet. And epsilon is our symbol for electromotive force. Electromotive force, or EMF. So you may have encountered the EMF in Year 11 circuits. It's generally provided by power packs or batteries or solar panels or generators will produce an EMF. It is measured in volts. Okay? So please recall, measured in volts. So if I was to give you the length of the wire, the strength of the magnetic field, and the distance, the speed at which we sweep that wire through, you can figure out the amount of voltage that might be set up across this wire. Okay? This, very similar to the Van de Graaff generator, in that the Van de Graaff generator has the rubber belt that basically rips electrons off. I believe it actually creates a positive charge on the dome. But for this example, let's just pretend that it deposits electrons onto that sphere, that top sphere. It's doing work. The electrons don't all want to be crammed up there. And every time you throw another electron up there, they gain more and more electrical potential. And so your Van de Graaff generators were actually used in the early 1900s to create high voltage. You can actually make particle accelerators with Van de Graaff generators. At this school, we just use it to make really cool sparks and make your hair stand on end. But you can accumulate thousands, tens, hundreds of thousands of volts of potential difference between the dome at the top and Earth. And so when you bring the earth rod towards it, you get that big spark as all of the charges dissipate and neutralize and travel through to Earth. Again, you can accumulate a charge here, and then you might be able, if you can encourage them, they might jump across and make little spark gaps. But this idea doesn't really give us much use. We'll look at how we can sort of harness the movement by maybe getting it to travel in a circle instead. And that way it's not really, you don't want your generator racing off with a certain velocity. We can have it spinning. Yes, Marcus Handley.
So we have work equals force times length. Where did displacement mean length come from?
So basically I'm forcing my electron from one end to the other. Okay? Now, I would like to show you underneath this diagram that Faraday's law is as follows. And this is the other equation. Faraday's law says that the EMF is going to equal the rate of change of flux with respect to the rate of change of time. That is Faraday's law. I've pretty much thrown it straight at you without any warning. But now I want to show you that the two equations on the board that are highlighted are equivalent. Where is he? There he is. They are the same equation. So I will attempt to show you that now. If we go back to this equation, in that diagram, if you take a wire and you sweep it across, you are actually producing a change in flux. The wire is sweeping out an area. We would say that the change in flux is going to be like the change in BA. Well, in that diagram, the field is constant. It's not changing. So really, it's B times delta A. Now, just to make this work, I would say that S equals V times T. That meaning the distance, horizontal distance that you sweep your length of wire is simply going to equal velocity times delta T. Maybe I could put a delta there instead. Sorry if you've already written T. Makes no difference. You know, delta S. Oh, look at that. Now we've got... Okay, now let's throw something down here. Our delta A could be written as L times V delta T, because have a think. V delta T is going to be L times delta S. Length times width is area. So, if I went and said that my change in flux is going to be B L V delta T, yeah? And then we do a little bit of dividey, which is different from cancely, we get VBL, which is the equation that we had at the top. Okay? So, take a wire, sweep it through. You are creating a change in flux because you are sweeping an area in a given time. Okay? And so if I could say, well, how much area are we sweeping, children? Well, you'd have to figure out the length and the speed in a given time second. Let's in 1 second, it would travel V units. Yes, Alex?
So we don't have to derive any of these?
No, so these two are in your data sheet. Okay? It gets tricky because remember we figured out in Friday's lesson that there's 3 ways that you can change a flux in a coil. You can change B, change A, or you can rotate the coil. So there will be some tricky questions where you have to figure out what's actually changing and at what rate is it changing. All right, so it does get a bit trickier than this. All right. Let's just go to this here diagram. They love doing these kinds of questions. A plane with a wingspan. All right, so let's just put in our L of 80 meters. And can we change east? I apologize for this question to be a bit simpler. Could we just change it to north, please? So plane traveling north with a velocity of 200. Now, obviously, I haven't given you enough information. So we're just going to recall that where we are in Perth, our magnetic field is kind of doing this. Where we have B north, and then we have B vertical. Okay. At an angle of about 66.4 degrees. So in this question, what we require is the perpendicular component. Our EMF is V B perp times L. We need the perpendicular component to the length of the wing. Okay. Well, it turns out if I was to draw my little plane, this guy is sort of facing north. All right. So if this plane was to fly overhead, plane wing. All right. He's actually perpendicular to the upwards, the vertical component. All right. So the question, here's the thing. You are not expected to remember the magnitude of the Earth's magnetic field at this point, nor are you expected to know the angle of inclination. It would be given to you. You might be given the angle and the magnitude, and you might have to do a side mission where you calculate the component that is perpendicular to the length of the wing. Or I'm just going to give it to you. Here we go. B perp, let's go 4.99 times 10 to the negative 5 Tesla. Upwards. Sweet. Then all we need to do, throw everything together. V times B times L, and we get 0.799 volts of electrical potential. That's the magnitude. let's try and figure out some direction. So we are looking down at the plane. Okay, so this is a top-down view of the plane over here as it is traveling north. So if we want the vertical component of the magnetic field, which direction is it acting? Is it going into the page or out of the page? Out of the page, good. The vertical component is upwards. We are looking downwards, so upwards is going to be out of the page. Let's just crudely represent that with a couple of symbols, of dots, which tell us that it's traveling through a section that's coming out of the page. There we go. All right, now I want you to pretend that you are a little lone proton strapped to the front of that wing, and you are traveling that way. We'll use our right slap rule to figure out which way our charges are going to be slapped. So, thumb points upwards, fingers coming out of the page. Which way does your palm push this positive charge? Right, very good. So we would say that the right side of the wing accumulates a positive charge. But really, what do we know? Huh? It's because the electrons are all moving off to the left side of the wing.
Wait, sorry, so how do we work out it was the right-hand side?
Well, just fire a proton in the same direction that the plane's travelling.
Mm-hmm.
Which way would it go? It would be forced right. In fact, it would travel in a circle, but it would be forced right of the right-hand rule.
But if I'm doing the right-hand rule now, what am I doing?
This is the right slap rule.
So you go off the...
So I want you to pretend that you're a proton travelling north in a field that's coming out of the page. It would be forced to the right.
Cool.
If it was a proton entering this field, it would do like a circular motion, but it's trapped in a piece of metal. It's not travelling in a vacuum. It's stuck on a sea of, what is it? A sea of positive ions. No, negative. Wait, what? No. Whatever. I'm talking about a positive charge. So we just use the right-hand rule to figure out which way it would get slapped. Okay? Again, someone could take their multimeter out, put a contact on one side and a contact on the other, and set their voltmeter, and it would read 0.799 volts of electrical potential. Okay? Now, as I said, this is of no use to us. So I saw a question once, and I like this question. Someone said, okay, that's 0.8 volts. What if we had like a jumbo jet where we tripled the size of the wingspan, have it travelling faster? We might get a few volts. We might be able to get a couple of little LED diodes running along the side of our wing. We might be able to use this EMF to power some lights. Turns out we cannot. Can someone give...
in the future.
Can someone give us the reason as to why this wouldn't work? Go.
Because the electrons won't flow down the gradient because it's still experiencing the force.
Well, the electrons would move all to the left.
Yeah, and they're never going to move back.
They're never going to move back. So I'll take that statement and go, we would need a circuit. You'd have to have your charge circulating around in order for this to work. There's not going to be any circulation. They're all just going to accumulate to the left.
If you fly in a circle, will it work?
No. Maybe we could, as the plane starts to move, the electrons all race one way. Maybe they might make the LED flash as they all race, and then the plane's cruising, and then when the plane stops, all of the electrons race back.
So every time,
But
so that voltage would change every time velocity changed, right?
yes.
So the actual voltage you'd be able to harness is the change in voltage.
Okay, let me answer this. Okay, I'll answer the question. Here's my diode. I did ask for a red diode, thank you. Here is my little diode. Okay? And you've got, well, one side of the wire is bent like that. And then inside the diode, you have this tiny little chip, semiconductor chip, where they've got to jump across. The length of the wing might be 80 meters, but the actual length of the diode is in the order of millimeters. So really, if I wanted to do a VBL, I've got the V, the diode's moving that way. I've got the B, but the distance, we're talking that length, not the wingspan. So again, the voltage across one side of your diode to the other is not going to be 0.8 volts. It's actually going to be like microvolts. We're not going to be able to get any useful voltage out of this scenario. Okay? Now,
Question?
no. No questions.
Okay.
We will have. I will set up more and more of these, guys. I will set up more and more of these demos to demonstrate Faraday and Lenz's law because it is quite strange. It's esoteric. What I also try and do is explain these phenomena about 3 different ways. Obviously, Wace wants the textbook explanation, but I also try and explain it using the right-hand rule, the right slap rule. Because this section of Lenz's law and Faraday's law and induced EMF, this is the trickiest part of the course that lots of Year 12 students struggle with. Now, what we have here is a brand new, lovely oscilloscope, digital 4-channel. It can save, we can beam it up to the projector. Apparently, it's Mr. Angus's new favourite toy. Before we look at, and it's going to show voltage over time. What I need you guys to look at is this wonderful diagram of a magnet with the magnetic fields that we drew at the start of the topic. You need to be able to draw field lines of a magnet. And there might be question 1 of the exam might be draw 8 field lines of a permanent bar magnet. And you've got to do the rules, symmetric, and go in the correct way. Now, for this context, I need you to have a look. I've drawn in the direction of the field, and I've also drawn in 2 regions. Justin, are you still talking? I can hear someone talking. Please look at this diagram. I now need you to appreciate that just beyond the north side of the magnet, the direction changes. And then just beyond the south side, the direction changes. So if I was to look at the direction of the field as I track from below the south edge to above the north, we go up to down, that's a change in magnetic field. Then from down to up, again, a change in magnetic field. And we know that a change in flux is going to be produced. If I was to put, say, a loop of wire, imagine I had a loop of wire here, and I move this loop of wire through the magnet, or I let the magnet move through the wire relative to 1, there's movement. In this area, there is going to be a change in flux. And it's generally around about the region where the pole edge of the magnet is. Okay? So as I move it through, there's a change in flux. As I move it through this region, there shouldn't be any change in flux because, again, look at these lines. They're pretty parallel in this region. There's no change in both density or direction. So if I take my hoop and I move it up and around in here, not much change. But then as I move it above the north edge of the magnet, again, whoosh, the direction changes by quite a lot. Okay? So, my first demonstration, I wish, was just a single loop of wire, but we'll have channel number 1. That's channel 1 apparently. I thought channel 1 was, that's not going to fit, so I need to use another magnet. Here we go. No, that's not channel 1, because channel 1. Oh, I have to press the button 1. Here we go. Alright, here is my. Ooh, look at that. I'll do it again. Alright, gents, I don't know which edge of the magnet, I could figure it out. So the south edge of the magnet in this coil, I'm very quickly going to remove it. And so what you're going to see is we would go from on the diagram there, we would have an up direction to 0. Ready? Here we go. Whoosh. And we get a peak. Alright? And so there, that is a voltage. Because Faraday's law says a change in flux in a given time period will induce an EMF. Okay? Now, I went from up to down, which is a change in down. So if I did it again, you're going to get that same direction. If I return the magnet, we get it downwards. Okay? So when I brought the magnet back, the change in flux was reversed. We went from no flux to upwards, which is a change in flux. Okay? Yes, Rahul?
If you leave it in that area.
Well, okay, let's give it a go. If I take this central magnet and I jiggle it backwards and forwards, you're getting a little bit, but what I really need, I don't want either edge to get close to that coil. I essentially want a single coil. But if I remove one, I get a flux. If I remove it that way, ooh, let's just let that ring. Let me just pass this magnet through. So we're going to go, here we go, in he goes, out he goes. We get a negative and a positive. Okay? And the reason is, the negative is when we went from up to down, and then the positive is when we went from down to up. That would make sense, wouldn't it? That the change, this change is one way, then the other change is in the opposite direction, which is why we get a negative voltage and a positive voltage. Okay? Now, let's have a look over here. Mr. Angus just set this up for funsies. Let's get this magnet on a spring doing that. And that's channel 3, I believe. Come on. Bear with me. There we go. Can we see our little sine wave there? Sorry if you're at the back. I'm new to this machine. I think I can increase it. There we go. We can increase it a bit. All right. Now, really, what we've got, this magnet, if it was directly in the middle, it's at the bottom now, and then I can bring it up a little bit. Oh, stop. Why did it stop? Friction? Oh, please. There we go. It's got a little bit of a jiggle going on, so we can't really get a perfect sine wave from this. If I try a bit harder, maybe I can. Not really. Not looking too good. Alright, let's just drop this back down a bit. What I want to show you are two possible ways. This is sort of a Mr. Murray prediction of the waste. Now, here I have a magnet on a stick. I'm glad Mr. Angus did this because he saw me with a metal one. If I place it in, and if I try and pass it through at a constant speed, when it enters and when it exits, we should get a nice sort of equal shape. The key here is constant speed, because when the north edge entered, it took a certain amount of time, and when the south edge left, it took the same time. Okay, because our magnet is nice and symmetric, and I passed it through at a constant speed. So somewhere on this booklet, either the back page or the front page, could you please draw the following? And I'm going to color code this. I'm going to put two different curves. Constant speed magnet through coil, we're going to get that shape. If you could please draw it. Alright, so the same time, and then you get the same change in flux, the magnitude I should say. You get the same magnitude change in flux. A north pole entering our coil will give the same magnitude of flux change as the south pole leaving. Obviously, the direction is reversed. So that's what we're going to say. We're going to get a positive voltage and then a negative voltage. Again, we could say the magnitude of our EMF is the same. Okay? So all things being equal, taking the same time, the same change in flux, but in a different direction, you should get a lovely symmetric curve. Any changes to that is basically my inability to move the magnet at a constant speed. Now, I need a volunteer from the audience.
Jasper volunteers.
Jasper, come on, let's get up here. Come on, Jasper. Now what I would like you to do is drop this bad. Well, actually, I actually don't. Yeah, I do need you here. No, I've got to press the stop. Now, hold on. Place the ruler in, and in just a moment. Now, don't do it yet. We're going to drop this. But what I need you now to appreciate is that when the north end enters, it's going to be travelling slower than when the south end leaves, because over this length, it's been accelerating. So have a little bit of a thinky think. How is that going to change our induced EMF curve? Alright, have a think. Delta T's, change in flux, magnitude of induced EMF, directions and such. Let me just make sure we're going the right way. Okay, are we ready? Whenever you're ready. Wow. Now, I don't know how to zoom out. So, oh, there we go. Zoom in. Enhance. Oh no. It seems to have locked off the top of it, unfortunately. But, definitely, I can see that the initial peak is over a much wider base. The second peak is much shorter. It has locked off the peaks, unfortunately. So, either on the same set of axes, or if you need to draw it again, I want you to draw a different colour. Something like that, if you can. So here, you've got your delta T initial and your delta T final, or let's say less than. Okay, and then also your maximum EMF initial is going to be less than, and my frickin' keyboard, go away. Flip and flip, there we go. So this is one of my sort of Mr. Murray waste predictions. It has occurred in the past where magnets have either been moved through coils at constant speeds, and they don't tell you how, whether it was strapped to a train set or they don't tell you, or it's dropped, or in one question it actually rolls down a ramp. And so there is an effect of gravity actually increasing the speed. The magnet was travelling slower when it entered, faster when it left. Okay? Now, for the time being, we're not going to worry about which side is actually positive and negative. Maybe after the exam we can come back and use Lenz's law to figure out which way the positive charge will flow, and then we can establish one side will be negative, one side will be positive. So for now, I've just said here's our convention. Okay? If charge flows this way, it's positive. One last thing. It's probably been about 15 last things this lesson. If you were to use SUVAT, V squared equals U squared plus 2AS, you would expect it to come out the end with a certain velocity. That's if there was no transfer of energy. But remember, as this is a voltage, right, across a coil of a resistance, there is going to be some power equals I don't know, IV or V squared on R, there is going to be some energy converted as the electrons race through a resistive wire. Some energy has been removed. And so it's not going to actually come out with that, it's not in free fall. That's the one thing we need to consider here. It's not in free fall because as it's moving, there's going to be energy being taken out. As I said, we will set up some examples for you to walk around the classroom after the exam, and you can literally feel the resistive force. As you try and move it, it suddenly feels heavier. As it's falling through, if you try to pull it through, you get this kind of upwards resistive force. That is you literally trying to pull billions and billions of electrons through a wire, but with just a magnet. So it's that whole spooky action at a distance. We're pushing electrons without actually touching them. We're making them interact with a changing magnetic field. Okay? So, if this question was to appear in the WACE, draw the two curves if you pulled it through at a constant speed versus if it was to fall, or if two ramps, one at a steeper ramp, one at a shallower ramp, and they want you to draw the induced EMF curve, I would be happy because I've quickly just mentioned these two different scenarios. So guys, over here, I know I did jump the gun a bit with our SIG-Gen oscilloscope, blah, blah, blah. Could you please have a look at these questions? They're very simple and they are only assessing VBL. So they're only assessing that VBL. Here's our little plane. Straight away, I just want you guys to do that whole thing. Imagine you're a proton on the wing, right slap rule. Which way does our proton get slapped? Or our positive charge, I should say. Thank you. Which side of the wing generates a positive charge? Left. Good. Okay, so it's still the right hand rule, but I'm just calling it the right slap rule. Same deal. You can use the VBL to figure out the magnitude, and you can use your right hand to figure out which direction or which side accumulates a charge. So could you please complete these questions? Oh wait, hang on. Let's look at question 1. Let's all look at question 1 together. All right. Stationary. Okay. If there's no movement, there can be no change in flux. So that won't happen. But if we bring a magnet near, then the flux is changing, either density or direction. Well, that's the same thing. Now this one, rotation. This question came up in the other class. Let's just quickly go over here. If you rotated, imagine we just had a uniform magnetic field, and I took a wire and I rotated it around. This is a bad view. Let's just look top down. So if I said top down, here's my eyeballs looking down. What would I see? I would see my wire and a bunch of dots. Very good. So now, imagine I took this wire and I just started spinning it. Okay? Now in the middle, at the pivot point, the protons, the positive, they're just moving around like this. They're not moving. They're stationary. But as you get to the edge, the further you get out to the edge, the faster you are traveling perpendicular to a field. So let's just use the right slap rule now. You're a proton on this edge and you're traveling this way with a speed. All right, what are we doing? Thumb goes down, fingers out of the page. Which way would you get pushed? To the center. So this is a really cool question because look what happens. The center would accumulate a positive charge, and each edge, let me just quickly check, right hand rule, Mr. Murray, thumb goes up, fingers, oh yeah. Each edge is going to accumulate, this is kind of like I don't know what you would call it, a double charge separation. So you've got a length of wire sort of spinning around. Now, if I took my voltmeter here and here, it would read 0, saying there's no difference in electrical potential. But if I went from middle to here, I would get a voltage. you might have to do a bit of an average. You'd say, well, the outside is travelling with a certain speed, the inside is travelling with a 0, and the speed would increase at a uniform rate from the middle to outside edge. Maybe we could take the average speed of one edge to find the EMF. Law of averages. Anyway, I just thought that a very lovely question. You spin a wire, and you get this very strange phenomena occurring, that electrons sort of go, and they go out to the edge. Each edge. Yes, Marcus.
If you viewed the field from the bottom, right?
Yes.
Then those dots would become crosses and nothing else would change.
Yeah, the rotation as viewed from the bottom would appear to be anti-clockwise. So you would do a flip-flip.
Yeah.
You'd still, your right-hand rule would still agree that the positive charges would get pushed to the centre. Cool?
Yes.
All right, get those questions done, and I will stop talking.